So moving on to our next module, we're going to look at the management of the processor. And this is after we've already looked at memory management and kind of an overview of operating systems. So what will we see in this module? Well, basically the process manager is responsible for allocating the processor to execute the instructions for incoming jobs. So this chapter is going to focus on single CPU systems, but chapter 6 is going to look at how this works in multi-core systems, and the same concepts can be used if we have a higher level scheduler. Single systems are the simplest, and the allocation becomes a little bit more difficult for multiple users, so we're going to start here. So the chapter starts out with some definitions, and these are handy to know in terms of understanding how this works. The first one is a program, and that's a unit of work that's been submitted by the user. Now, this is an inactive unit, for example, a file stored on disk, and it's not a process. A process is different. It's an active entity that requires a set of resources, including the processor and special registers, in order to perform its functions. Sometimes this is known as a task, but it's an executable program single instance. A thread is a portion of a process that can run independently. And so multi-threaded systems can have several threads running at one time with the same or with different priorities. And so that is a concept known as multi-threading. So you can have actually separate threads that do different things. So for example, with a web browser, one thread could retrieve images while another sends and retrieves email, and they're kind of operate independently of one another, yet part of the same job or the same program. Multi-programming is a technique that allows a single processor to process several programs residing simultaneously in main memory and interleaving their execution by overlapping I/O requests with CPU requests. The processor is allocated to each job or each process for a time period and then deallocated in an appropriate moment. And this is kind of a tricky task, so we'll see some of the details that go into that. An interrupt is a hardware signal that suspends execution of a program and activates the execution of a special program known as an interrupt handler. And context switching, something I have to do a lot. That's the act of saving a job's processing information in its PCB or process control block, so they can be swapped out of memory. And completed jobs are finished or terminated jobs. So there's an example found on page 105 where you're assembling a bicycle. Now you're building up your bicycle, you complete steps 1 to 3, and as you're completing step 3, your neighbor is mowing the lawn, they slip and they get injured and they call out for help. This kind of issues you an interrupt, and you grab your first aid kit, marking off where you were in terms of completing the bicycle. Okay, so on step 4. You go and help your neighbor, and then you return to assembling the bicycle, starting with step 4. So what was the interrupt? Well, that's kind of the neighbor's cry for help. How does this correspond to multi-programming? We're doing 2 things at once. Context switching is going from assembling the bicycle to administering first aid. And the completed job after you've helped the neighbor would be the rendering of first aid would be the completed job. So a single processor may be shared by several jobs or processes, requires a scheduling policy and a scheduling algorithm. For dual, quad-core, or other multi-core CPUs, more than one processor or core can be located on a chip, and a single chip can contain multiple cores. And we've kind of talked about this before, this distinction between the individual processor and a set of cores. So the scheduling processor or scheduling manager has a bunch of sub-managers. The process manager has a bunch of sub-managers. We'll talk about 2 to get started. And this is a hierarchical scheduling system that takes place on 2 levels. There's the job scheduler, which is the highest level one. It's responsible for scheduling the jobs, and it has initiation based on certain criteria. And then there's process scheduler, which is the lower level of the 2. It takes care of scheduling the individual processes, determining the execution steps, and these are also based on certain criteria. So what the job scheduler does is it selects an incoming job from the queue, places in the process queue, decides on the initiation criteria, and then it has a scheduling algorithm and a priority. And that's kind of these design decisions we make when we're designing or putting together an operating system. The goal with the job scheduler is to sequence the jobs to achieve efficient system resource utilization. And that's what we can do is we can balance IO and computation. So, if computation is busy, then we can, schedule some things that are IO interactive and vice versa. And so the idea is to keep the system busy most of the time. The process scheduler is lower in the hierarchy. It assigns the CPU to execute individual actions, jobs that are placed on the ready queue by the job scheduler. So it determines the job to get the CPU resource, when and how long, decides on interrupt processing, determines queues for job movement, and recognizes when a job is finished or when the job is terminated and we have room for more. It should also exploit common computer program traits. And again, programs alternate between these two cycles, CPU and IO intensive. So they can have general tendencies. Maybe a job is more IO intensive, or maybe it's more CPU intensive. But in general, they alternate between those two cycles. If you think back to CS1, when we talked about, what is the way that a general sequential program works, you set up your variables, you get input, you perform some calculations, and produce output and finish up. So that's your basic procedural program. Well, the getting input for the variables, that's IO. The doing the calculations, that's CPU, and then switching back to IO. So, here's an example of a simple procedural program. Ask the user for the first number, retrieve the first one that's entered, ask for a second number, retrieve the second number, add the first and second number, divide the sum by 2, and then multiply by 12 to get an average for the year. Print the calculated average and print the average for the year, and then finish up. So in looking at this, you'll be able to determine which ones are the IO cycles and which parts are the CPU cycles. So in terms of CPU cycle times, there's a greater number of jobs requesting shorter CPU cycles and fewer jobs that request long CPU cycles. So that's another thing that can play into our design decisions. There can be a third sub-manager, and that's the middle level scheduler, and that's kind of a third layer. And this is found in highly interactive environments that handles overloading by removing active jobs from memory to reduce the degree of multi-programming and context switching. And this allows other jobs to be completed faster. So it removes things and places them in queues. So what states does a job and a process go through? So basically, it changes as it moves through the system. It starts in holding, goes to ready, waiting, running, and then finished. And of course, it can transition between these different states. So here's what typically happens. The user submits a job. The job is accepted and placed on hold and placed in the queue. The job state changes from hold to ready, indicates the job is waiting for the CPU. Changes from ready to running when the selected for the CPU and processing, and then it changes from running to waiting. If it, for example, tries to get something that's not available at this time, then we can put it back into a waiting state. And then eventually, after it's finished running, it will change to finished. Well, how does it transition from one state to another? It depends a bit on which transition. From hold to ready, that's based on the job scheduler that has a predefined policy. For ready to running, it's when the process scheduler initiates using a predefined algorithm. Running back to ready initiates according to predefined time limit or other criteria. You're using too many resources, or hey, something has a higher priority, you need to kind of wait for it to run. From running to waiting, this is initiated by an instruction in the job. Waiting to ready, this could be the scheduler initiates a signal from the IO device manager, or if we say, okay, the IO request that you initiated is finished, then the job can continue. Because remember, IO is kind of the slowest part of the von Neumann architecture. And then running to finished, basically after we're done and we figure out that this is the end of the process, then we can, our job, then we can go from running to finished and free up resources for the next job to come in. So here's what it looks like visually. We start in that hold state that's controlled by the job scheduler as to whether it gets into the ready state, goes into running state from there. If you have an interrupt issued, then it can go back to the ready state. IO request or a page fault, hey, we didn't get the right instructions. We have to fetch those from memory, which is kind of more of an IO thing than a something that happens inside the processor. Then it goes into that waiting state. From waiting, once we finish up the input output we need to do, then we can go back to ready. And finally, we can go to the finished state. So likewise, threads, and again, these are the portions of the process that can run independently. They also have states, and they have 5 states as they move through the system: ready, running, waiting, delayed, and blocked. So the application creates a thread. It gets placed in the ready queue. Going from ready to running, it assigns it to a processor. Then running to waiting when it's dependent on an outside event. For example, hey, I'm waiting for user input, or I'm kind of an event handler, or I'm waiting for another thread to finish. Then I can be waiting. From waiting to ready, the outside event occurs or the previous thread finishes. Running to delayed. So application that delays the thread processing by a specified amount of time. Delayed to ready, the prescribed time has elapsed. Running to block, an IO request is issued, and then block to running, your IO is completed. So that's kind of like the queue, the waiting that we had with the jobs. And then running to finished, when we're all finished with that thread and it terminates, then we release all the resources and make room for another one to come in. So when the operating system is working with threads, it needs to be able to create new threads, set up a thread so it's ready to execute, delay threads for a specified amount of time, block, suspend the ones that are waiting for IO, set threads to a wait state until a specified event occurs, schedule them for execution, synchronize the thread execution using semaphores. We're going to get into semaphores a little bit later. And terminate a thread and release its resources. So here's what the state diagram looks like. And again, this is quite similar to the one with the jobs, a little bit different. So this brings us to control blocks, and these are kind of like the like a passport. They have a lot of information about the job, and so this is a data structure that represents each process, and it's called a process control block, and works a bit like a passport. So when the job scheduler accepts a job, it creates this, and then it gets updated as it moves through the states. Similarly, each thread also has a control block that's known as the thread control block. So what's in there? Probably the important one to know is the process status word, and that's the current instruction counter and register contents when the job isn't running, but is either on hold or ready or waiting. And so this is important for when you're doing context switching. You have to save where you're at and be able to come back to it. The program counter, register contents, main memory, resources, priority, those should all be fairly self-explanatory. For the threads, we need the program counter and the register contents, its priority, pointer to the process that created the thread, and all the other threads created by this thread. So threads can spawn more threads. Probably seen that in 350. Queues use control blocks to track jobs the way that customs officials use passports to track visitors. The control blocks contain all the data needed by the OS to manage the processing of the job, and the process control block gets updated as the job moves through the system. Data in the process control block can be used to resume a job. If it's the current block rather than the actual process that's linked to the other control blocks to form the queues. So next time we'll take a look at scheduling policies and algorithms.